Welcome back, everyone. So today we're going to be talking about electrochemistry. So as the name implies, we're going to be learning about chemistry, right, which is what we've been learning about all this time. But obviously now we're going to add in electricity. We're pretty familiar with how electricity works, right? We've all seen a lightning storm. We've walked across a fuzzy carpet with our socks on and then touched a doorknob and gotten shocked, right? So electricity is just the presence and flow of electrical charge. And that charge has to be carried by a charged particle. It could either be a negatively charged electron or a positive or negatively charged ion, but we need something in order to carry that charge. Okay, so electrochemistry is just studying how chemical energy, which is stored inside the bonds of our atoms and molecules, right, that's going to be interconverted into electrical energy. And we know that you can never create or destroy energy, just like you can never create or destroy matter. So it makes sense that that electrical energy has to come from somewhere. And we're going to learn about where it's coming from. Okay. Now, in the case of what we're going to call a redox reaction or an oxidation reduction reaction, these are reactions that involve a transfer of electrons. Okay, so let's look at a pretty standard example here. So we've got two elements. We've got sodium and chlorine. And notice that there's nothing up here in the right-hand corner of those, right? So in other words, those currently have zero charge on them. Makes sense, right? They're just normal elements just doing their thing. And then at the end of the day, though, sodium's going to end up with a positive charge, and chloride, now has a negative charge, right? And so we can clearly see that we went from something neutral, in the case of sodium, to something positive, and in the case of chlorine, something neutral to something negative. So we definitely moved around electrons. And we can write what are known as half reactions. So if I take a sodium atom, it can give up an electron to become a sodium ion, okay? And I can also take a chlorine molecule, and each one of those chlorines can grab onto another electron to become chloride ions. Okay, so those are called half reactions. We're going to deal with those later. To balance this, because there are, two electrons that are involved in each of these, it makes sense that I would need to, kind of balance this thing out, put a 2 in front of everything. Okay, but we'll get to that in just a minute. Okay. And so here we have oxidation and reduction occurring. Now, what does that actually mean? Okay, well, let's see, there we go. Okay, there's a little acronym that you're probably familiar with, which is oil rig. And remember that oxidation is loss of electrons, and reduction is gain of electrons. It's a pretty easy way to remember it, right? So in our case, sodium went from having 0 charge to having a +1 charge, right? So we can clearly see that it lost an electron along the way. Since oxidation is loss of electrons, sodium was the element that was being oxidized in this case. On the other hand, chlorine went from having 0 charge to having a -1 charge, so it clearly gained an electron along the way. So chlorine is what's being reduced. Okay, so pretty simple, right? Now, one thing that's also quite simple, but sometimes people get confused on it, is when we talk about oxidizing agents and reducing agents. So an oxidizing agent is whatever is doing the oxidizing, okay? It is not what is being oxidized, okay? That's an important distinction there. Just like the Terminator goes out and terminates others, the Terminator isn't himself terminated, okay? So same thing happens here, right? Sodium is being oxidized, okay? We agree on that, but that means that it's actually doing the reducing. So sodium is actually the reducing agent. And then chlorine is being reduced, so it must be the oxidizing agent. Or in other words, if I want to oxidize something, I'm going to mix it with some chlorine because that's going to cause the chlorine to be reduced, and in the process, it's going to oxidize something else. Okay, awesome. So in our case with sodium and chlorine, we went from two neutral elements to elements with charges, right? Anions and cations. And so it was pretty easy to see that something was being oxidized and something was being reduced. But oftentimes it's not quite so easy to see that. And so that's where oxidation numbers, or sometimes called oxidation states, come into play. You probably heard about this before. You might have remembered last semester we talked about this, but so we're going to go through it again, though, just because we're going to need it now. All right, so oxidation numbers are just a bookkeeping method. It's a way of kind of, keeping tabs on where our electrons were and where they're going and so forth, so we can see what's being oxidized and reduced. Now, it's important to note that these are not real charges, okay? The confusing thing is that if something has a charge, that's also going to be equal to its oxidation number, but just because something has an oxidation number doesn't mean that's its charge, okay? So let me give you an example. A sodium cation has a +1 charge, so therefore it also has a +1 oxidation number, okay? On the other hand, if I have something like sulfur trioxide gas, in that case, sulfur is going to end up having a +6, a +6 oxidation number, but that does not mean that the sulfur actually has a +6 charge, okay? Charges are discrete things that you can actually measure in the lab, but oxidation numbers are they're like accounting, right? It's just our way of keeping tabs on where our electrons are, okay? The other thing is that charges can never be fractions, right? You can never have like a 1/2 charge, because that would mean you lost half of an electron, which doesn't make any sense. But you could have fractional oxidation numbers, okay? They're generally just small whole numbers, either positive or negative, so ranging from about -6 up to about +6 is where they're generally in the range. But you might have a -2/3 oxidation state, and that's perfectly legal, okay? It's just the way it is, okay? Awesome. So how do we assign these? Well, first off, we're going to go through a set of rules, and we always apply these rules in order. So start with number 1, and actually that's confusing because it says 1 there. Okay, there's 4. All right, so always start with number 1, and then go down the list until you, basically until you're done, right? So I'm going to go through the rules, and then we'll apply these, because that's the best way to do it. All right, so first off, any free elements are automatically set at 0. So if it's just oxygen gas, 0. If it's iodine crystals, 0. If it's aluminum, 0. Sodium, 0, right? As long as it's just a free neutral element, it's automatically set at 0. If you have a monatomic ion, so something that's just like a chloride ion, has a -1 charge, so it also has a -1 oxidation state, or oxidation number, okay? The next thing, the next 2 rules are 2-part rules. So number 3 says that the sum of the oxidation states of all atoms in a compound is equal to 0. What that means is that if I were trying to come up with the oxidation numbers for water, so for hydrogen and oxygen in water, I would know that I would have 2 hydrogens, and whatever their oxidation number is, plus the oxidation number of the oxygen, and that those would have to add up to 0, okay, by definition. Now, on the other hand, if I had, in 3b here, it says, okay, what if you don't have a neutral molecule? What if you had something like a sulfate ion? Well, in that case, I would have to take the oxidation state, or oxidation number of my sulfur, plus the oxidation number of 4 different oxygens, and that would all have to add up to a -2, because the charge is -2. So you're always just looking in the top corner. Here, there's no charge, so it adds up to 0. Here, it's a -2, so it adds up to -2. Okay, pretty simple, right? And that's useful because, for instance, we're going to learn in a later rule that oxygen likes to have a -2 oxidation state, right? So in this case, if I were to say, okay, I've got sulfur plus 4 oxygens, and if each one of those oxygens has a -2 oxidation number, then a little bit of algebra allows me to solve for the oxidation number of sulfur, which in this case, let's say I'd have to add 8, so that'd be a +6. So sulfur would have a +6. Okay. We'll also learn in rule number 5 in just a moment that hydrogen likes to be a +1. Okay, so if hydrogen's a +1, then it would be 2 times a +1 plus oxygen has to equal 0. So that would be 2 plus oxygen equals 0. So therefore, oxygen must equal -2, right? Oh, I should not do that. I'm getting confused between my zeros and my O's. Okay, so oxygen would be a -2 in that case. Okay, so that's how we would solve for these things, is you simply start applying the rules to elements in your compound, and then at some point, you're going to have only one element left in your compound, and then you use algebra to solve for it. So again, we'll see that in just a minute. Okay, rule number 5 is a table. And I know tables are a pain, but it's just what you have to do with it. So, so in this case, fluorine is automatically assigned a -1, okay? And then hydrogen, then oxygen, then the rest of your halogens in group 7A, then group 6A, then group 5A, right? And you just kind of start at the top of the table, work your way down until you have something that, that doesn't have an oxidation number, and then you can solve for it. So for instance, let's say that we were dealing with nitrogen dioxide. Okay, and I wanted to know what's the oxidation number of each of those elements. So what I would do is I'd first start with rule number 1. I don't see any free elements, no monatomic ions. Rule number 3 says that my nitrogen plus my 2 oxygens have to add up to 0, right? Because there's no charge up in this corner right here. So they have to add up to 0. Okay, what about rule 4? No, I don't see any group 1A or group 2A elements. So then I need to move on to rule number 5. And rule number 5 says, okay, well, start at the top. I don't have any fluorine. I don't have any hydrogen. Oh, I do have oxygen, right? So go ahead and give oxygen a -2. So nitrogen plus 2 times -2 equals 0. So nitrogen minus 4 equals 0. So nitrogen, in this case, must have a +4 oxidation state. Okay. Now notice that if we had kept going down with the rules, we'd say, wait, nitrogen's in group 5A, so it should have a -3. But we have to apply those rules in priority, right? And so oxygen gets its -2, and then nitrogen gets stuck with the +4. So that's just kind of how it is, right? It's kind of like when you're on a plane and you're way back in the back of coach, and the stewardesses come through and they start handing out, ginger ales and packages of pretzels and whatever. And the people at the front, they get whatever they want, right? They're first class, so they get their choice. And then as they slowly work their way back, then it's like, okay, fluorine, you get your pick. Okay, you want a -1? Good, you get it. Hydrogen, what about you? You want a +1? Oxygen, you get a -2, right? And you keep applying those, giving them what they want. Nitrogen was way back here in the very back. And so even though it wants a -3 oxidation number, it got stuck with the +4 because that's what was left over, right? It's like, yeah, you get that tomato juice that no one wanted. Okay, so same type of thing. Let's go ahead and try applying this with a few others. See if it makes sense. So let's look at some reactions, because that's generally how things work, right? Okay, so first off, do we have, let's see, rule number 1 was any free elements? Well, yes, we do. So here we've got oxygen. So let's assign that as 0. I don't see any other free elements there. So let's move on to rule number 2. Any monatomic ions? Well, they're not actually free ions, right? So we'll just keep going. Although we could go ahead and look at this and say, you know what, potassium likes to make a +1 ion, right? That's kind of a lousy one. So let's go ahead and assign that. Chloride happens to be a -1, so we can assign that. And then we have to keep going. We still have this ClO2 over here. And so rule 3A says that the potassium plus the chlorine plus the 2 oxygens has to add up to 0, right? Because notice that there's no charge up here in the top right-hand corner. Okay, so we've already decided that potassium gets a +1, okay? So now who's next? Chlorine versus oxygen. Let's go to rule number 5. let me erase some of this stuff just so it's out of the way. So chlorine versus oxygen. Well, let's start with fluorine at the top. Nope, hydrogen. Oop, oxygen comes next. So oxygen gets defined as a -2. Okay, so we can go ahead and erase this oxygen here. Let's replace that with a -2. So that means you've got 1 plus chlorine minus 4 equals 0, or in other words, chlorine minus 3 equals 0. And so therefore, chlorine must have a +3 oxidation number. Okay, and again, notice that in the table, normally would give chlorine a -1, but it was last on the list, so it didn't get its pick. It gets stuck with the +3. And again, these are not charges. That chlorine in that molecule does not actually have a +3 charge, but we're bookkeeping our electrons, okay? Cool. Let's try another one. So let's do the same thing here. Okay, we've got a zinc. Zinc is a 0 because it's a free element. Oh, we also have a silver that's a free element right here. Okay, and then what about the rest of them? Well, turns out that these are all ions at this point. Chloride's a -1, which means silver must be a +1, so they cancel out. Chloride's a -1. Zinc must be a +2 in this case, right? Because you have 2 chlorides that are canceling out that zinc. So in that case, it was pretty easy to just go down the list and just using our rule for free elements and our rules for monatomic ions, we could assign all of those. All right, now what about if I was asking you what was being oxidized and what was being reduced in each of these cases? So then what I would do is I'd say, okay, look at this potassium. Potassium's going from +1 to +1. It did not change its oxidation state at all, right? Chlorine went from +3 down to a -1. So chlorine is being reduced in this case. Okay. What about oxygen? Well, oxygen went from a -2 up to a 0, right? So you can see how you went from a negative up to a 0. So in that case, oxygen is being oxidized. Okay, it's increasing its oxidation state. So that's another way of looking at oxidation or reduction. Oxidation is increasing your oxidation state. Reduction is reducing your oxidation state. Makes sense, right? Okay. Now remember that reducing could be going from a positive down to a smaller positive value, or from a positive to a 0, or it could even go from a 0 to a negative, or from a negative to a more negative number, and vice versa for oxidation, right? Okay, what about in this case? Well, our chloride didn't do anything, right? Chloride went from -1 to a -1. So it wasn't oxidized or reduced. Silver went from a +1 down to a 0, right? So in that case, silver was reduced. Okay, zinc went from a 0 up to a +2. It increased, right? So in that case, zinc is being oxidized. Now, you could also do this in terms of oxidizing agent versus reducing agent, right? Since silver is being reduced, silver is the oxidizing agent. And since zinc was being oxidized, zinc must be the reducing agent. Awesome, right? Let's try a couple more. Okay, so again, just like always, let's go through and look for free elements. Oxygen, 0. Nitrogen, 0, right? So they're just neutral elements by themselves. All right, now let's go ahead. I don't see anything from rule number 2, no monatomic ions. We do know that the sums of the oxidation states will have to add up to 0. I don't see any group 1A or group 2A, so now I need to start assigning these. So hydrogen, near the top of the list, right? So let's go ahead and assign that. So hydrogen gets a +1. Hydrogen gets a +1. Okay, that means that nitrogen is going to be stuck with whatever's left. So nitrogen +3 times 1 equals 0. So nitrogen +3 equals 0. So nitrogen, in this case, gets a -3. Let's go ahead and assign that a -3 there. What about this oxygen over here in water? So it's got to be 2 times a +1 plus oxygen equals 0. And I should be consistent, make those zeros whenever I'm dealing with oxygen. So that means, let's see, 2 plus oxygen equals 0. So therefore, oxygen equals a -2 in this case. Okay, so we can see that nitrogen went from a -3 down to, or sorry, up to a 0, right? So in that case, it is being oxidized. And on the other hand, oxygen went from a 0 down to a -2. So it is being reduced. Okay, so just like we were doing this before, we're doing the same thing here. Okay, let's go ahead and try another one real quick. So if you want, you can pause the video, try these yourself, and then check it, right? All right, so aluminum's by itself, iron's by itself, so those get zeros. And this is a cool reaction. This is called the Thermite reaction, where you take rust and aluminum, mix them together, ignite it, and you end up getting aluminum oxide and iron. But the really cool thing is this is an extremely exothermic reaction. The iron actually comes out as molten iron, which I think is pretty cool. All right, so let's see. What else do we have? Well, if we keep going down these lists, we'll eventually find oxygen, and we're going to give oxygen a -2. Let's give oxygen a -2 in both cases. That means that the iron and the aluminum have to get stuck with whatever's left over, right? So in this case, it's got to be 2 iron, and then it's +3 times a -2 equals 0. So that means that 2 iron minus 6 equals 0. So 2 iron equals +6. So that means each iron must have a +3 oxidation state, right? And you probably could have just eyeballed that and figured it out. We do the exact same thing over here, right? 2 aluminum +3 times a -2 equals 0. So 2 aluminum minus 6 equals 0. So 2 aluminum equals 6. So each aluminum, therefore, must have a +3 oxidation state. Okay, so we can see that the iron went from +3 down to 0. So in that case, it's actually being reduced, right? Because it's lowering its oxidation state. Aluminum, on the other hand, went from a 0 up to a +3, so it is being oxidized. Or in other words, aluminum is the reducing agent, iron is the oxidizing agent. Okay, so pretty simple, right? It's going to take some practice. Go ahead and try some of those. You can just look at literally any compound and go ahead and assign oxidation numbers to it. All right, now here's where things get a little bit tricky. Okay, we're going to be balancing some redox reactions, and it takes a couple of steps, okay? Because it's a bit different than balancing normal equations. All right, so just kind of be prepared for that. All right, so the first thing is assign oxidation states. Okay, determine what's being oxidized and what's being reduced. This isn't technically actually necessary. You can do it without determining what's oxidized and what's reduced, but it's a nice way to kind of check yourself. We'll see how to do that in just a second. We're then going to write what are known as half reactions. I kind of showed you that way up here at the beginning, right? These are technically known as half reactions. We're looking at the oxidation half and the reduction half of our overall reaction. Then we're going to balance those half reactions. So, and we do this in a very specific order. First, you balance anything other than hydrogen and oxygen. Then you're going to balance oxygen, but you can't just add in O's. You have to add in water, okay? Now, unfortunately, that means you're also adding a bunch of H's, right? So then you have to balance your H's by adding H+. And then, if it's in acidic or neutral solution, you just stop there. But if it specifically mentions that it's in basic solution, then we have to neutralize our hydroxide with some, or sorry, our hydrogen ions with some hydroxide. I'll show you how to do that. And then you add in some electrons, and then we're going to possibly have to multiply our half reactions by something in order to make them balance. Then you add them up to make sure they cancel, and then you just check yourself, right? So 7 steps, kind of weird, let's practice. Okay, so first thing, let's assign some oxidation states. So we don't have any free elements. We do have something that's a monatomic ion, so let's go ahead and assign that a +2. And then we'd start going down the list, and as we go down the list, we would see oxygen. So let's go ahead and give oxygen a -2. All right, so if we give each of these oxygens a -2, then that actually shows us that we really only have one element that's missing an oxidation state in each of these molecules, so we can go ahead and figure those out. So let's go ahead and do that. So let's start with C2O4 2-. Well, we have 2 carbons, and then we've got 4 oxygens, so 4 times a -2 would be a -8, and we know that that has to add up to -2, right, based on our charge there. So that means 2C equals, let's see, we add 6 to that, 8 to that, so that's going to be a +6. So that means that each carbon has a +3 oxidation state. Okay, that one looks good. Let's do the same thing for our manganese dioxide. So we don't know what manganese is yet, but we know that 2 times a -2 is -4, should add up to 0. Okay, so that means that manganese must have a +4 oxidation number or oxidation state. And then same thing over here with carbon, right? Carbon plus 2 oxygens. If each oxygen's a -2, that's -4, should add up to 0. So carbon, again, must be a +4, okay? Excuse me. So we went ahead and figured out the oxidation numbers for each of these. So I'm going to go ahead and erase all of that. You can go back and slow down the video if you need to go through those again, but you've seen a bunch of them. So our next step is we need to go ahead and go through these steps right here. Okay, so we've assigned oxidation states. Next, let's go ahead and write our half reactions. So first, let's go ahead and take our C2O4 2-, and we know that that's turning into CO2. Right, so we're just kind of tracking the carbons through, basically. So now let's balance everything but hydrogens and oxygens. So in this case, it's just the carbon. Let's put a 2 here. That gives us 2 carbons, and it gives us 4 oxygens, which is perfect. So that's how we normally kind of balance an equation, right? But our next step is we need to balance the charges. So notice that we have a -2 charge on the left-hand side. So we're going to need a -2 charge on the right-hand side. It's currently neutral, right? There's no charge there. So what we're going to do is we're going to go ahead and add 2 electrons to this. So that gives us a total of a -2 charge on the left, -2 charge on the right. Okay, so now we're going to do the same thing with our other half reaction. We've got MnO2, and that's turning into manganese 2+. Okay, now at this point our manganese is already balanced, so we don't need to do anything with that, but we do need to add oxygens. We need to add 2 oxygens to the right. Now we're not allowed to just write 2 oxygen, okay, because you can never have just an oxygen atom floating around like that. So what we need to do instead is we need to add oxygen in the form of water. So we're going to add 2 H2O. Okay, and again, if we go back to this, it just says, okay, add H2O wherever oxygen is needed. That's the law. That's what we have to do. Okay. Now the problem with that, though, is that not only, well, we did add 2 oxygens, but we also added 4 hydrogens to the right-hand side. So we need to go back and add 4 hydrogens to the left-hand side. But again, we can't just add hydrogen atoms, so we actually can add hydrogen ions because we know that every solution is going to contain some hydrogen ions, okay? And so at this point, we now have 4 hydrogen, 1 manganese, 2 oxygen, 2 oxygen. So everything is balanced except for our charges, right? So notice on the left-hand side, we have 4 positive charges. So we have a +4 charge over here. Here we just have a +2 charge. Okay, so to make those balanced, the only thing we're allowed to do is to add some electrons. So we're going to go ahead and add 2 electrons to the left-hand side. All right, because that way it balances out. So now we've got a -2 and a +4 on the left, cancels out to a +2. On the right, we just have a +2. Now, I mentioned previously that you don't actually have to assign oxidation states, but it is a good way to check. So here's how we check. We notice that our manganese here went from a +4 down to a +2. And so it would make sense that if this, to go from a +4 down to a +2, we must have had to add 2 electrons to it, right? So that makes sense. So it's a good way to check. We can do the same thing with our carbon up here, right? So carbon, we had 2 carbons, each going from a +3 up to a +4, okay? That means that each of those 2 carbons must have lost 1 electron, okay? And since there are 2 carbons, it makes sense that we have 2 electrons there. So again, not essential that we do that oxidation number portion, but it's kind of a good way to check. It's also nice because it allows us to determine if it even is a redox reaction. If it's not a redox reaction, just balance it the normal way, okay? All right, so now the next step, if we go back to this, is we've done oxidation states, we wrote the half reactions, we balanced them. Notice that we didn't have to do this portion because it doesn't say that it's in basic solution. So we don't have to neutralize our hydrogen ions with hydroxide. So if it's neutral or acidic, we can just keep it as is. And this one didn't specify, so we can assume that it's neutral. All right, we added balanced our charges of the half reactions by adding electrons. Now we need to make sure that the number of electrons in both half reactions is the same. Okay, now in this case, we're lucky because we have 2 here and 2 here. So they already are the same. But if they weren't, we might have to double or triple one of them in order to make them the same. So what we're trying to do is we're trying to make sure that these 2 electrons exactly cancel out these 2 electrons, so that when we add the reactions together, that they end up canceling out. Okay, kind of like when we do a Hess's law or something like that, we add the 2 steps together and we cancel out anything. Now that we have that, we add the half reactions together, cancel any like terms out. So let's do that. So we've got, let's see, it looks like 4 H pluses. We've got a C2O4 2 minus, and we've got a MnO2. It does not matter what order we put those species, right? Then we've got 2 carbon dioxides over here. We've got a Mn2 plus, and we've got 2 water molecules. We double check that there is nothing on both sides that should cancel, right? So for instance, if we had 2 water molecules on each side, we could cancel those out. But we don't have any of that, so in this case, we are officially done. So that would be our answer for this question, right? And then in step 7, we would just go through and double check everything, right? So 4 hydrogens, 2 times 2 is 4 hydrogens. We've got 2 carbons, 2 times 1 is 2 carbons. We've got 1 manganese, 1 manganese. We've got 4 plus 2 more is 6 oxygen. So we've got 2 times 2 is 4, plus another 2 times 2 is 1, so that's 6 oxygens there. And then the last thing we should always do is check our charges. So we've got a +4 here, right, because 4 positives, plus we've got a -2 here because of that charge there. So that should be 4 minus a 2 is a +2 charge on the left. And then on the right, this thing's neutral, this thing's neutral, this one's got a +2. So we've got a +2 charge on the right. We actually don't care what the charge is on both sides as long as it's equal, okay? So at this point, we're done. That's officially our balanced equation right here. I'll just erase some of this stuff just to declutter it, but that is our official balanced redox reaction. A little bit of work, right? Let's go ahead and do a couple more just for practice, because it is a little tricky, right? So first off, notice that in this one, it specifies that it's acidic. Okay, that just means that we don't need to cancel out our hydrogen ions. Okay, so let's go ahead and do the same thing that we've always done. Okay, now for this one, just to show you that it's possible that you don't have to do the oxidation states, I'm not going to bother on this one. Okay, I'm just going to go ahead and split these up into 2 different reactions. So I've got my CrO4 2 minus turning into Cr3 plus. Okay, my chromiums are already balanced. I do have 4 oxygens I need to add on the right-hand side. So let's add 4 water molecules. But notice that in the process, I just added 8 hydrogens. So let's add 8 H pluses over here. Let's look at our charges. We've got a positive 8 and a negative 2, so that adds up to a positive 6 on the left, and we only have a positive 3 on the right. So we need to make those charges balance each other. Now remember, we're not allowed to add positive charges, but what we can do is we can add negative. So let's go ahead and add 3 electrons to the left-hand side, because when we do that, that ends up making this a positive 3 instead. It dropped our charge by 3. Okay, so that looks pretty good. Let's go ahead and do the other half reaction. So in this case, we've got NO2 turning into NO3 minus, of course. So we just drop those down. Our nitrogens are already balanced. What about our oxygen? It looks like we need an oxygen on the left-hand side. So let's go ahead and add a water molecule to the left. That gives us 3 oxygens on both sides. But now we have 2 hydrogens on the left, so we need to add 2 hydrogens to the right. Okay. Now that's balanced all of our different atoms. Now we need to balance the charge. So it looks like we've got a negative 1 over here, and we've got a negative 1 and a positive 2 here. So that comes out being a positive 1. So that means that we're going to have to add 2 electrons to this, right? Because if we add 2 negative electrons, that'll drop it down to a negative 1 so that these two will be equal. So I need to add 2 electrons to this side. Now again, one way to kind of check that you're doing this correctly is one of these has to be oxidation and one half reaction has to be reduction. I personally don't bother like labeling which one's which or anything like that, but I do check to make sure that I'm adding electrons on the left-hand side of one and adding electrons on the right-hand side of the other. If I'm adding it, both to the reactants or both to the products, I know I've done something wrong. Okay, so at this point, I've gone through most of the steps, right? I don't need to do step 3D because it's not basic solution. I've balanced the charges of my half reactions. Now I need to make the number of electrons in both half reactions the same. Okay, so this is one where we will have to do this step because notice that in the top reaction we've got 3 electrons, in the bottom one we have 2. So what we need to do is we need to go ahead and make these equal. So what I'm going to do is I'm actually going to double the top reaction. So this becomes a 6, this becomes a 16, this becomes a 2, this becomes a 2, and this becomes an 8, right? So all of those are now doubled. That gives me 6 electrons on the top. And so on the bottom one, I'm going to triple it. So I'm going to put a 3 here, a 3 here, a 3 here. 3 times 2 is 6, 3 times 2 is 6. Because what that does, it allows me to cancel out my 6 electrons on both sides. And that's essential. They have to cancel out. Now at this point, I can drop everything down. It looks like I've got, and again, it doesn't matter what order, so 16 H pluses. I've got 2 CrO4 2 minuses, 3 water molecules, 3 NO2 minuses. This is a big one, right? Let's see, we've got 2 of these, we've got 8 waters, and we've got 3 nitrate ions and 6 hydrogen ions. That's a lot of stuff. Now, luckily, some of it's going to cancel out because notice that I've got 6 hydrogen ions here. So let's go ahead and cancel out 6 of them. Let's just make this into a 10 instead. Okay. Same thing with water. It looks like I've got 3 water molecules over here. I've got 8 here, so I can cancel out 3 of those and make that into a 5 instead. And then once I've done that, now I can officially drop everything down and write the equation. So 10 hydrogen ions, 2 CrO4 2 minuses. Our water's canceled out, so now 3 nitrites, 2 chromium, 5 water, 3 nitrates, and my H is canceled out, so bam, everything's done, right? So that would be my officially balanced equation. Again, I could double check that I've got 10 hydrogens on both sides. I've got 2 chromiums on both sides. I've got, let's see, 3 nitrogens, check. I've got 2 times 4 would be 8, plus another 6. That's 14 oxygens on the left. 5 plus 9 is 14 oxygens on the right, so that looks good. And then last but not least, check my charges. I've got a positive 10 here. I've got 2 times a negative 2 is a negative 4. 3 times a negative 1 is a negative 3. That comes out to a positive 3 on the left. On the right, I've got 2 times plus 3 is plus 6, and then 3 times a negative 1 is negative 3. So that ends up being a plus 3 on both sides. So that looks great, right? Everything balanced out, my atoms, my charges, everything. So now I've got my officially balanced equation. Okay, so I know these take a while, right? It's just the nature of it, but some of them are a little easier than others. Let's go ahead and try another one. Okay, if you feel comfortable with it, you can skip this part of the video. If you want to test yourself, go ahead and just pause it and write out this, figure this one out, and then you can check yourself. But let's go ahead and work through it. So this one's pretty easy because I know this is a 0, this is a plus 1, this is a 0. Oxygen's a negative 2, so a chromium minus 8 equals negative 2. Chromium must be equal to a plus 6 in this case. So again, you don't have to do that, but it's a nice way to double check yourself. Okay, so now let's split these up. We've got chromium turning into CrO4 2 minus. Our chromiums are already balanced. Let's go ahead and add 4 water molecules on the left-hand side, which then of course means that we need to add 8 hydrogen ions on the right. Okay, what else? Well, that one looks good, except we need to do the charges, right? So we currently have a 0 charge on the left-hand side, and on the right we've got a negative 2 and a positive 8, so that gives us a positive 6. So that means that we're actually going to have to add in 6 electrons over here, right? Because if we add in 6 negatives, that'll give us 0, and then things will be balanced. So plus 6 electrons. It's a lot of electrons, but if we want to double check to see if that's correct, notice that we went from a 0 all the way up to a plus 6, right? So that chromium must have lost 6 electrons in the process. So in that case, it's kind of nice that we did our oxidation numbers, because it allows us to double check. Okay. Now, before I do that, technically I've skipped a step, right? I forgot about this one. It is in basic solution, so I actually do need to cancel that out. Okay. So let's go back. Here we are. So let's go ahead and, before we do that, it actually doesn't matter what order, but just to stick with what I'm doing, I need to get rid of those 8 hydrogen ions, because in basic solution, which this is in, I can't have a bunch of H plus ions floating around, right? Those would immediately react with 8 hydroxide ions. Okay. Now, if I add 8 hydroxide ions to the left, I also have to add 8 hydroxide ions to the right. That's going to keep my charges the same on both sides. It's also going to keep my number of hydrogens and oxygens the same on both sides. Now, the key thing here is that those 8 are going to turn into 8 water molecules, right? Because H plus OH equals H2O. So what I can do now is I can just erase all of these and instead just draw in 8 water molecules. Okay. Now when I do that, I can go ahead and calculate my charges again, and I'm still going to find that I have to add 6 electrons to this. Okay. I think in the past I've been doing it in red, so let's go ahead and do it in red again. Okay. Next, let's do the other half reaction. This one should be really easy because all we have is silver turning into silver ion, right? So in this case, literally everything is balanced except for our charges. So what I'm going to have to do is, let's see, I've got a plus 1 on the right-hand side and a 0 on the, oh, I just messed that up, right? I was just checking to see if you're paying attention, because notice that, so actually this is actually a good illustration. So when I'm doing this, if I were to go and do my charges, I'd say 0 and a plus 1, and then I'd think, oh, I'm going to have to add an electron over here, right? So that there's a -1 to cancel it out to 0. So I would add my 1 electron here. And when I went to do that, mentally I said, wait a minute, I've got electrons on the right-hand side of both of them. That can't be right. So I must have done something wrong. And sure enough, when I went back and looked at it, I said, wait a minute, my silver on the left-hand side is a silver ion, and the silver on the right is neutral. So that actually saved my bacon, because that means that when I add an electron, I have to add it to the left this time, because that way they both cancel out to 0. So now it looks good, right? Now I've got electrons on the right, electrons on the left. So the next step is I need to make sure the number of electrons is equal. So on the top I've got 6, so why don't I go ahead and just multiply everything by 6 here? Because that way my 6 electrons will cancel out. Okay, now I can go ahead and just drop everything down. So I've got 8 hydroxides, 4 waters, got a chromium, and 6 silver ions. And now I've got a CrO42-, 8 water molecules over here, 6 silver over here, and that's it, right? And this one actually nicely illustrates why we have to do these weird steps when it comes to electrochem, like redox reactions, is because if I was just balancing this normally, there's no way I would know that I need 6 of each of those, right? I would say, well, they're already balanced, so don't mess with them. But this tells me that in order to get the number of electrons that I need 6 of those silver ions to be reduced into silver metal, okay? All right, and then again, I could double check all of my atoms, all my charges to make sure they're correct, but it looks good to me. Okay, one last one, and I know we're doing a ton of these, and I normally don't do that many examples, but this is a lot of steps, right? And it's kind of a pain, so I just want to make sure that you feel good with it. All right, this is acidic, so that means I don't need to do that annoying hydroxide step. So instead, let's go ahead and, again, we'll try one without doing our oxidation states. So here I've got SO3 2- turning into SO4 2-. Looks like I've got, let's see, I've got 3 oxygens on the left, 4 on the right, so I'm going to have to add a water molecule. Ooh, what am I adding for? Let's add a water molecule over here. But that does mean that we need to add 2 hydrogens over here, right, to make it balance. Next, let's check our charges. We've got, let's see, a -2 on the right, and we've got a -2 and a +2, canceling out to 0. So we're going to have to add 2 electrons to this right-hand side so that it'll cancel out, right? So that this will add up to a -2. Okay, that looks pretty good. Let's do our next one, which would be our copper 2+, turning into copper 1+. Okay, again, just like the last one, this step's really easy because our copper's already balanced. We don't have to worry about hydrogen or oxygen. So all we need to do is balance charges. On the left, I have a +2. On the right, I have a +1. So that means I'm going to need an electron on that left-hand side so that it'll balance out to just a +1. Now, I said that it was acidic, so I don't have to cancel out any hydrogen ions that I have. So the next step I need to do is simply, let's see, I can just make sure that they have the same number of electrons. So let's go ahead and double this bottom one so that I have 2 electrons, because that way my 2 electrons will cancel. And now I can just add everything up. So I've got a water molecule, SO3 2-, I've got 2 copper 2+, I've got a sulfate, 2 hydrogens, and 2 copper 1+ ions. Okay, again, it doesn't matter what order you write those in as long as you've got reactants on the left, products on the right. And at that point, you can double check to make sure everything, has the appropriate number of atoms and charges. It looks like it does. So we're good, right? So hopefully that's starting to make some sense, that you kind of have to go through those. And again, I just want to mention, just real quick again, that some people are very, very particular and they always do step 1, not actually essential. okay? Also, another thing that sometimes people will do is they will actually do this step right here, where you're neutralizing things. Sometimes they'll actually do that way down here after you've added things together. They'll add the half reactions together, cancel things out, hoping that the hydrogen ions will cancel, and then if they do, you don't have to worry about them. But if not, then you have to do the hydroxide thing. So again, different ways to do it. It all comes out to the same thing, but whatever works for you is fine. Okay, so finally we can go ahead and change to something else. So what we're going to look at now is what are known as galvanic or voltaic cells. And this is kind of actually interesting that they have these two names because galvanic is named after Luigi Galvani, an Italian physicist, and voltaic is named after Alessandro Volta, who is an Italian physicist and chemist. And they were actually pretty big rivals because Luigi Galvani, he came up with this idea of animal electricity. So he basically like take a frog's leg and he would attach maybe a piece of zinc to one side of it and then maybe a piece of copper to the other side of it. And he would notice that the frog's leg started twitching. And so he said, oh, look, these animals are producing electricity, and that's what's happening here, right? Because he could actually measure a change in, the current moving through it. And then Volta came along, and he's like, I don't think it has to do so much with the frog. I bet you could use anything that conducts electricity. And so he substituted the frog's leg with just brine-soaked paper, basically paper soaked in salt water, and found the exact same thing, that you still get this electrical current flowing through it. So it really had nothing to do with the frog's leg itself. And they became kind of bitter rivals for a while, but it's kind of funny that now we call these galvanic cells and voltaic cells. So both of them get their ideas. Now, Volta kind of wins out because, we talk about volts and so forth. So anyway, so the idea is that we have looked at this reaction or similar reactions. Like if I take a piece of copper wire and I put it into a silver ion solution, what will happen is that the copper will actually start dissolving. And you can see this. You can see that these are blue copper 2+ ions that are literally dissolving off of the metal and into solution. But then in the process, you'll also notice that silver solid starts being formed, and we're literally getting chunks of silver that are coating the wire and kind of falling down to the bottom. So that's solid silver metal. So we know that we're moving electrons from the copper to the silver, right? We're oxidizing one and reducing the other. And so the idea is, what if instead of just allowing this to, just popping the wire into solution, what if we force these electrons to move through an external wire, right? We know that the electrons are trying to get from the copper to the silver for some reason, which we'll talk about later. So we know that they're moving from one metal to the other. So why not take advantage of that, right? It's kind of like if you have a stream and the stream's moving downhill through your farmland, and you're like, well, I know the water wants to move downhill. Why not make it do some work for me? You put in a water wheel and it spins the water wheel for you, and the water naturally does it just because it wants to get downhill. So we're doing the same idea here. So this is where we can make batteries. It's the whole idea behind a battery. So the idea is that any spontaneous redox reaction can serve as the source of electrical energy in our battery, right? And what we're going to do is instead of just putting the two half reactions together, putting the copper and the silver together in the same vessel, we're going to compartmentalize them. We're going to separate them into two half cells. And then we're going to force the electrons to move through a wire in order to light up a light bulb or do whatever we want, charge run our phone. And what we're going to see is that we're going to get oxidation at one of our electrodes. Okay, and this is called the anode. This is easy to remember because oxidation starts with the vowel and anode starts with the vowel. Okay, so oxidation occurs at the anode, and then reduction is going to occur at the other electrode, what we call the cathode. And again, reduction and cathode both start with consonants, so pretty easy to remember that. And what's going to happen is the electrons are going to move from the anode, from whatever is being oxidized, to the cathode where things are being reduced. And as those electrons kind of move through the wire, that movement of electrons is electrical energy, right? So this is what it would actually look like, okay? So we can use that same reaction that we saw before. We've got a chunk of solid copper, right? That's our copper anode. And you can see that as the reaction takes place, it starts to form copper ions in solution, okay? Now those electrons, they have to move, right? They have to move from the copper. They're going to move through this wire, through the voltmeter, okay? And then, or through a light bulb or whatever we wanted, and then down into the silver, okay? And then at the silver cathode, this is where silver ions are going to start plating out and forming solid silver metal, okay? Now, a couple of things have to take place here, right? We know that electrons are moving, kind of clockwise through this. And so we have to have something that allows for this electrical charge to kind of flow in a circle, right? So what we end up doing is we have something called a salt bridge. And in the salt bridge, this just allows ions. Oftentimes we'll use sodium nitrate ions. So the nitrate ions, because of their negative charge, start moving through this direction, right, to get towards the anode. And that's actually why we call it the anode, is because the anions are attracted to it. And then we've got sodium ions, which are in solution, and they are going to try to move towards the cathode. So cations move towards the cathode. It makes sense, right? And so because of that, it allows for this nice little circular circuit, hence the name, to occur, and then we literally have a battery at this point. Now, one of the issues that can occur, though, is, in this case, we're using solid copper metal and a solid silver electrode, right? And that's fine as long as they're both solids, but what about some of these? In this case, notice that this is an ion, and so that is an aqueous solution if we were to write our states here. This is aqueous, and this is aqueous, right? And so in this case, we don't have any solid electrodes that we can use. And so what we'd have to do is we'd have to use an inert electrode, okay? Like a graphite electrode or something, something that doesn't actually react, but just gives a surface, a solid surface that you can attach your wire to on each side, and then also that allows for transfer of these electrons to actually occur. Okay, not a big deal, but in the lab, that's what you'd have to do. Okay, now you can probably imagine that you can't use just any two metals, right, or any two species to do this. Because what if we tried to switch it? What if we had, what if we tried to have the copper gain electrons and plate out, and the silver to start losing electrons? Well, we'd be trying to push it in reverse, okay? And so this difference in electrical potential energy between our two electrodes, our anode and our cathode, is called the cell potential. You can imagine that some things really, really, really want to get rid of electrons. For instance, sodium really doesn't want to be sodium metal. It wants to give away an electron, right? And then there are other metals, like, for instance, gold or platinum, that don't want to exist as ions. They really want to exist as solid metal, okay? And so if you partnered those two things up, you would get a really strong battery, right? You'd get a lot of potential for this battery to generate energy because you've got a lot of electrons that are moving as fast as they can to get to the other electrode, right? Whereas if you had two things that had very similar, difference, a very small difference in potential energy, you can imagine your battery wouldn't work very well because it just wouldn't want to convert over, okay, and kind of move electrons from place to place. So we can measure this. It's called the cell potential, and because you can't have oxidation without reduction and vice versa, you can never measure just like half of a cell at a time, right? So I can never know what's the true, like potential energy of a copper electrode, right? And so what you end up having to do is you have to, measure this versus what's called a standard hydrogen electrode. We'll talk about that in just a second. But But we can write what are called the standard EMF, or electromotive force. And this one, it's not written very well because of this, but it looks like this. So our E cell, E naught cell, I guess. And this is just under standard conditions. This allows us to kind of compare the two things, the anode and the cathode reaction. I've already talked about the salt bridge, right, that you typically use like sodium nitrate or potassium nitrate, just something that allows for ions to flow through. Okay, now before we get into calculating all of these cell potentials, we also need to understand something called cell notation, which is just a way for us to represent what is happening in our electrode, in our cell, okay, at the two different electrodes. And so the way this works is that we are always going to have oxidation on the left and then reduction occurring on the right-hand side of our thing, right? So oxidation's occurring here, reduction's occurring over here on this side of it. Alphabetical, right? So that kind of helps. And then we're going to use these lines, and these lines, if it's a single line, that means that we've got a phase boundary. So the best thing is to look at this example down here. So first off, notice that we've got iron turning into iron 2+ ions. So it's being oxidized, right? It's increasing its oxidation state. Notice that we're going from a solid to an aqueous solution. So we have to put a solid single line right here to represent that phase boundary. If we're going from a solid to a solid, we would just use a comma, okay? So over on this side, notice that we're going from aqueous to aqueous, so we just put a comma there instead. In fact, we also happen to, because these are both aqueous, we can't have an electrode made out of an aqueous solution. So in this case, we're actually using a hydrogen electrode, okay, which involves platinum metal because it's very inert, it doesn't do much, and then hydrogen that's going from hydrogen, to H2. So again, notice commas in between anything where it's just aqueous to aqueous to aqueous. But then when we go from aqueous to solid, we put in a phase boundary line, okay? And then in the middle, between the two electrodes, we're going to put two of these lines to represent our salt bridge, okay? So that's what's happening. So let's go ahead and just try one of these, see if we can make sense of it. All right, so for this one, let's go ahead and try to write out our cell notation for this. So what's actually happening? Remember, we want oxidation, and then we want our salt bridge, and then we want reduction. Now, luckily, most diagrams are drawn with the oxidation on the left, but not always, so you should always double check. But let's see what's happening. We've got copper that's turning into copper 2+, right? So in that case, yeah, this is definitely oxidation, right? So I'm going to write copper, and it's a solid, and then it's turning into an aqueous solution, so I need to put in a single line there. Then it's going into copper 2+ ions in the aqueous phase because it's dissolved in water. And then I've got my salt bridge here in the middle. And then what's happening on the other side of this? Well, it looks like I've got silver ions that are turning into silver metal, right? So again, silver ions dissolved in aqueous solution, turning into solid silver metal. So just like that, right? So that would be my cell notation for this cell. Okay, so notice also that this happens to tell me on the voltmeter what the cell potential is for this, right? Assuming that everything's at 1 molar concentrations and all that, it tells me the difference between the copper and the silver, right? It basically tells me that copper really wants to give up electrons and silver really wants to take those electrons, and so I end up with a positive 0.46 volts, okay? Positive is good, it means it's spontaneous in the forward direction. So I mentioned this before just so you can kind of see what I was talking about is if I have two things that are both in the aqueous phase, like in this one here, obviously I can't have an electrode made out of two different ions. So instead what you have is this thing where you've got this little kind of glass tube that you're piping hydrogen gas into, and that hydrogen gas just goes through here, kind of bubbles out into solution, which we don't really care about. But what matters is that we also have this platinum electrode right here. Again, it's inert, it doesn't do anything, but it provides a nice surface for the reaction to take place. Okay. Also, it gives us somewhere good that we can attach this wire, because otherwise how are you going to make a battery with no wire? Okay. And so at that surface, what you're seeing is that the hydrogen gas kind of sticks onto the surface of it, and then the electrons end up reacting with the hydrogen ions and reducing those into hydrogen gas. Okay. And so because of this, we call this the standard hydrogen electrode, or SHE. And all of our cell potentials, right, our E naught cell is measured against this, right? This is kind of our standard. So we're basically saying this is equal to 0. This is our benchmark. And then things that are that want to be reduced, they're going to have a positive value because they want to be reduced more than hydrogen does. Things that want to be reduced less than hydrogen does, or in other words, they want to be oxidized rather than reduced, then we're going to give those a negative value for our reduction potential. So there are tables of these. You should never memorize these. These would have to be given to you, either on a table on the homework, or you can look them up on an exam. Obviously, I'd always give you the values. Okay, but a couple things that we should note on this. So first off, note that here's our hydrogen being reduced into hydrogen gas. And note that we give that a defined cell, our E naught value, our reduction potential of exactly 0 volts. Okay, we just had to set something at 0, so that's what was decided. Okay, anything that that is listed below this hydrogen will actually dissolve in acid, because what happens is if I have something like lead, for instance, okay, if I take lead metal and I put it in something like HCl, I'm going to end up getting lead chloride plus hydrogen gas. So I'd have to balance that and put a 2 there, but you get the idea, right? And so, and the reason that this reaction takes place is because the lead wants to give away electrons, and hydrogen wants to gain those electrons, because lead's down here, it's below hydrogen, so it actually is more willing to give up electrons than hydrogen is. So hydrogen will take those electrons. Things that are above H plus on this chart won't react. So for instance, silver. You put a chunk of silver in hydrochloric acid, nothing happens, right? And so that's actually, it's interesting because you'll notice that we've got platinum, we've got gold, okay, and silver, as well as copper. So those are commonly used as coins, right? That's why we've used those for thousands of years as coins, is because they don't react. A lot of other things like lead, some things down here, like if we tried to make coins out of manganese, or let's see, if we tried to make coins out of sodium or even aluminum, it would react with acid. And so those would end up dissolving, whereas things like gold, platinum, silver, and copper won't. Now, most of those, you can trick them into reacting with acid, but you can't use just a normal strong acid like hydrochloric acid. You actually have to use like nitric acid, because what's actually happening there is you're not reducing the hydrogen, you're actually reducing the nitrogen instead, which is kind of weird. And then something like gold, notice the gold's way up here, it really doesn't want to react with it. And so what'll end up happening is you will have to use something called aqua regia, which is a mixture of hydrochloric acid and nitric acid. And so it will actually dissolve gold. In fact, there's a chemist back during World War II. There were 2 Jewish Nobel Prize winners who were worried that that they would lose their Nobel Prizes, or just 2 Nobel Prize winners, and that they were worried that the Nazis would come in and confiscate their gold medals that came with it. And so this chemist, he actually dissolved their gold medals for them, put them in just beakers of acid sitting on his shelf in his lab, and then when the Nazis came, they didn't find any gold. And then after the war was over, he precipitated back out the gold, sent it to the Nobel Prize people, and they recast the medals for them, which is kind of cool, right? Okay, what else is interesting about this chart? Well, it turns out that this right here is pretty important, okay? So any reduction reaction, there's a typo there, is spontaneous when paired with the reverse of any of the reactions listed below it on the table. Okay, so that means, for instance, that if I take iron and I pair it with the reverse, right, aluminum turning into aluminum ions, that I'll get a reaction, right? So in other words, iron ions will turn into iron metal as aluminum metal turns into aluminum ions. And that's the basis of the thermite reaction, okay? All right, so useful table, but again, don't memorize it or anything, just be aware of how to use it. So be aware that what we would need to do is be able to look at these reduction potentials on the right-hand side. So what we can do with this is a couple of different types of problems. The first would be something like this. We can determine which of these would act as a good oxidizing agent. In other words, which of these things really, really, really wants to be reduced, okay? Something really wants to be reduced if it has a very high, a very positive E0 value, okay, reduction potential. So what we would need to do is we would have to go into our table and figure out what's the reduction potential for each of these, okay? So I just pulled these up so I don't have to keep flipping back and forth, but iodine is positive 0.54 volts. Calcium is a negative 2.87 volts. And these values might be slightly different than the ones on the table. I used a slightly different table when I pulled these, but they should be almost identical. 1.498 volts for gold, and then chromium 3 plus is a negative 0.74. Okay, so looking at these, my best oxidizing agent is going to be something with a very high reduction potential, right? So it looks like, in this case, gold is the highest, right? It really, really, really wants to go from gold and be reduced into gold metal, okay? Which makes sense because gold doesn't like to dissolve and form an ion. Okay, second, it looks like iodine is pretty good. It's also a positive value. Next, we'd have chromium 3 plus. It's negative, but at least it's not super negative. And then the worst one would be calcium 2 plus. So this would be our worst oxidizing agent. Okay, again, because we're just going from the most positive to the most negative reduction potential. Now, what if on here, what if they listed something like just gold by itself, not a gold ion? So what I'd have to do is I'd have to go back here, and going from gold 3 plus to gold is a positive 1.498, which is what I wrote, right? But if I want gold turning into gold ions, I would have to do the reverse. So for this, it would be a negative 1.498 volts, okay? So if you're going the reverse direction, you got to flip your sign. So in this case, the very worst oxidizing agent, or actually it wouldn't be the very worst, calcium would still be worse, but we could go ahead and plug our gold metal in right there, okay? Now what if the problem didn't want a good oxidizing agent? What if you wanted a good reducing agent? Well, if it's a good reducing agent, you want something that really, really, really wants to be oxidized, right? And so in that case, these would be the best reducing agents down here, and these would be the worst reducing agents. So remember that anything can be oxidized or reduced, right? But some of them just really want to be oxidized and some want to be reduced. And really it just comes down to stability, right? Something like gold is more stable when it's a gold solid than it is when it's a gold 3 plus ion, okay? And so that's where all of these factor in, okay? So that's the first type of problem you could have. The second type of problem that you could have would be to determine if your reaction itself is spontaneous, right? So for instance, could I make a gold cathode and then an iron anode? Would that work? I don't know, right? We'd have to calculate it out. And what we'd have to do is we would have to look at the E0 value for our cathode and our anode, and then take our cathode and subtract out the anode. And then if that overall cell potential is positive, then that means it's a good cell, right? It's a good battery. It's a spontaneous one. Otherwise, if it's not, it's non-spontaneous, and we should actually flip it, right? And make our cathode out of, iron, for instance, and our anode out of gold. And so let's go ahead and try a couple of these and see if these would work, okay? So first one is we've got silver ions turning into silver metal and chromium ions turning into chromium metal turning into chromium ions, okay? So what I would have to do is I first need to determine what's being reduced and what's being oxidized, right? Because remember that our formula is E naught for the cell is equal to E naught for our cathode minus E naught for our anode. And then remember that what this really means is cathode, C and R both start with a consonant, whereas A and O are both vowels. So what we need to do is figure out which one is where reduction is occurring and where's oxidation occurring. So we've got silver turning into silver metal, right? So in that case, that means that that must be reduction because we're going from a +1 down to a 0. Okay, so in that case, this is definitely reduction. Okay, so what I would do is I would go ahead and look at this on my chart, right? And I'd find out that the E naught reduction potential for this is equal to about positive 0.80 volts. Okay, now let's do the same thing for our oxidation. It's chromium turning into chromium 3+. And so this must be oxidation. Sure enough, we're going from a 0 up to a +3, so it is being oxidized. So our E reduction potential for this is equal to a negative 0.74 volts. Okay. All right, so that is our reaction that's taking place, right? Now, a couple of important things. Oh, actually, let me go ahead and finish this calculation, and then I'll tell you some important notes. So E naught for our cell is going to be equal to the reduction one, our cathode, which is a positive 0.80 volts, minus the oxidation one, right, which would be a negative 0.74 volts. Okay, so E naught for this cell would be equal to positive 1.54 volts. It's a positive value, therefore this is spontaneous. Okay, that would make a good battery. And it would have quite a high cell potential, right? This would work quite well. Get a high voltage off of this. Okay, so what are a couple of things that are important to note? Okay, the first thing that's important to note is that in our case here, notice that it was actually 2 silver ions turning into 2 silver metal. Okay, what we do not do is we never ever double or triple this thing. So don't multiply that by 2. Don't ever do that. Okay, these reduction potentials are intensive properties, so it doesn't matter how much of it you have, right? It doesn't matter how much. I could have a small chunk of silver, it would have a reduction potential of positive 0.8 volts. If I have a big giant mountain of silver, still 0.80 volts. Okay, it's intensive just like density is. I wouldn't say, well, I have 1 gram of water, so it has a density of 1 gram per mil, but if I have like 10 grams of water, it's going to have a density of 10 grams per mil. No, it wouldn't make any sense, right? So the same thing here. So that's one important thing to note. The second important thing to note is that when I looked up my chromium turning into chromium 3+, it's actually going the opposite way, right? So here, chromium 3+, so I'm going in reverse. Now you have 2 options when you do this, right? What I did is I just went ahead and took the negative 7.4, right? And then I just wrote it exactly as is, right? Because this formula here takes into account that you have to flip your sign, right? Because you're subtracting out the anode. In other words, you're just flipping the sign on it, okay? Because I did a negative of a negative. So that's one perfectly valid option. The other option you could do is you could purposely flip the sign and make it a positive 0.74 because you saw that you had to flip the reaction and then just add them together. Either one, totally fine, okay? But that's the general idea. So let's go ahead and do the same thing for our nickel. Okay, let's go ahead and erase all this stuff real quick. Okay, so let's go ahead and write out our reduction reaction. So reduction is where it's decreasing, right? So it looks like it's nickel 2 plus going to nickel metal. And so the E reduction value of that on the table, you have to make sure that you go exactly from nickel 2 plus to nickel, right? So for instance, with the chromium, you want to find the one that says chromium 3 plus turning into chromium, not something where you're going from chromium 3 plus turning into chromium 2 plus, because that's not what's happening in our half reaction, right? So in this case, it happens to be a negative 0.26 volts. Okay, let's try our oxidation reaction. So this would be lead turning into lead 2 plus. The E reduction potential for that is a negative 0.13. I didn't flip the signs or anything because I'm using this formula up here in the top right-hand corner. So I know the E cell for this is going to be equal to my cathode, my reduction one, right? Negative 0.26 volts minus, in this case, a negative 0.13 volts. So E naught cell for this would be equal to, it looks like a negative 0.13 volts. It's a negative value, therefore this is non-spontaneous. It wouldn't work just by itself. If I hooked up this, to a voltmeter, it wouldn't work. I wouldn't get a voltage. It'd be like a dead battery, right? And so what would happen is I would actually want to do the reverse of this. I would actually, if I wanted to make a good battery, I'd have to take nickel metal and lead ions and then go the opposite direction to make lead metal and nickel, right? I'd have to go reverse, and then I'd flip the sign on it. It would be a positive 0.13. It wouldn't be a very high voltage, but at least it would be spontaneous at that point. So what you're probably noticing is we're talking a lot about spontaneity, right? And we've talked about spontaneity before. We talked about it with K, right? We said that if K is greater than 1, a reaction is spontaneous, right? We also talked about our Gibbs free energy, and we said that if delta G is negative, spontaneous, right? And we just learned one more thing, that if our cell potential is positive, spontaneous, okay? And so therefore, you could do the reverse. If you want to know if it's non-spontaneous, it would have a negative cell potential, it would have a positive delta G, it would have a K less than 1. And because of this, there are ways to convert between all of these. We've already seen this equation, right? Negative RT ln of K, that's our delta G naught value right there. And it turns out that we now are learning two new equations where we can go from our cell potential into our delta G, or we can go from K into our cell potential, or vice versa for all of those, right? But those have some weird terms that we're not quite familiar with. So let's go ahead and look at each of those. So first off, we've got this equation right here, right? And this, we know what delta G is, right? Standard free energy change. We know what our cell potential is, our standard cell potential that we just learned about. We've seen N before, right? Just like PV equals nRT, N is our number of moles, but this time it's the number of moles of electrons. Very important, okay? So, for instance, if I was going back to one of these equations here, I would see that my N value would be 2 because it was 2 electrons, right? Here, my N value was 6 electrons. Here, my N value would be 6 electrons. Here, N would be equal to 2 electrons, right? So it's always going to be a positive value, but it all depends on how many moles of electrons are moving through this. Okay, so that's one big factor that we have to factor in there. The second is our Faraday constant. So this is a constant right here, 9.648 times 10 to the 4th. Sorry, that should be a superscript there. Okay, joules per mole per volt, right? Okay. Now notice that we do put a negative sign in here, and that explains why if delta G is negative, our E for our cell has to be positive, just because of that negative value right there. Okay, now we also could go ahead and go between our K value and our E naught value, right? So K, we already know what that is. We know how to calculate it. And so here again, we've got our Faraday constant, number of moles, we've got our temperature in Kelvin, and we've got our R value, which is this 8.3145 joule per mole Kelvin. Okay, so those all factor in. Now, sometimes if you're feeling kind of lazy, you can actually kind of simplify all of this, right? Because under standard conditions, which would be 25 degrees Celsius, 298 Kelvin, then we can put this thing, and this thing all together, because they would all be just numbers, right? And we could use this equation right here, 0.0592 volts divided by N, the number of moles of electrons, times the log of K. There's a slightly different version that involves the natural log. Different scientists will use different ones, but that's the basic idea. But again, this only works if it's at standard conditions, right? So at 25 degrees Celsius. If not, you better use the full one. You can always use the full one. I mean, it doesn't hurt. You'll always get it right, but sometimes people like to shortcut it. Okay, so notice that if we're factoring in K, remember that K is equal to like product concentration over reactant concentration. And so, sure enough, concentration does have an effect on our cell potential. So if I want my reaction to become more spontaneous, I can increase the concentration of a reactant, or I can decrease the concentration of a product. This is nothing more than Le Chatelier's principle, right? If I make a big mountain of this, it's going to naturally shift to the right. It's going to be more spontaneous in the forward direction. If I remove some of my product, it's going to naturally try to fill in that hole, and it's going to increase my voltage, right? It's going to become more spontaneous. My reaction will want to go forward. And of course, you could do the opposite. All right, so we're almost done here. Let's just finish up with a famous equation called the Nernst Equation, and that's where we can factor in our delta G value, and we can do this under, kind of at equilibrium, right, which is what we saw before. If things are at equilibrium, we can do that. But what if it's not at equilibrium, right? Well, just like always, if it's not at equilibrium, instead of using K, what do we use? Q, our reaction quotient, right? But then we have to factor in what it would be at equilibrium, right? So that's where we factor in either our delta G naught value, our E naught cell potential, right? And then we'd factor in our Q value for each of those. Okay, so let's go ahead and see that one in action, because that one is a little more than just a very simple plug and chug. So let's try one of these. Okay, so here we've got our reaction, platinum metal turning into platinum ions, iron ions turning into iron metal. We've got our concentrations for these. We've got a temperature, it happens to be at 25 degrees Celsius, and I even was nice enough to go ahead and give you the reduction potentials for each of those. And I also wrote out Faraday's constant, just so that we can remember it, because that's one that I never remember. It's only used in this chapter, never use it again, so it's kind of a pain to memorize it. All right, so we have concentrations, and we're not told that this is at equilibrium, right? So if it's not at equilibrium, we're going to have to use the full thing. We're going to find this, our cell potential is going to be equal to our standard cell potential, okay, minus our RT over NF, and then natural log of Q, okay? Now, we could cheat a little bit because it is at 25, but we'll just plug in everything just to make sure we've got it. All right, so we're going to have to calculate a few things before we do this, right? So first off, we know that we're going to have to calculate our E naught value, okay, so that we can plug that in. So how do we get E naught? Well, we just learned that, right? We saw that our E naught for our cell is equal to E naught for the cathode, or the reduction reaction, minus E naught for the anode, okay? So our iron is being reduced, right? Because it's iron 2+, gaining electrons, becoming iron metal. So that's going to be our cathode. So that means that E cell is going to be equal to, and I guess I should put cell up here if I want to be particular, but all right, so that's going to be a negative 0.44 volts. And then we need to subtract out the other one, which will be this right here. So we're going to subtract out 1.18 volts. So our standard cell potential in this case is going to be equal to about negative 1.62 volts. Okay, so in this case, that's a really crappy cell potential, right? It's highly negative, which means that it's not going to happen. So this is not spontaneous. But let's go ahead and plug these in. So -1, well, actually, at standard conditions, it would not be. But it could be under these conditions. We have to find out. So we've got our negative 1.62 volts there, okay? We can go ahead and erase all of this stuff because we've already used it. Okay, and then what else do we have? Well, it's going to be negative R, which we said was 8.3145, and that would be joules per mole Kelvin. Okay, we've got T, which has to be in Kelvin, so that's 298 Kelvin. We've got N. How many moles of electrons? Well, it looks like 2 moles of electrons are moving back and forth. So 2 moles down here times our Faraday constant here, 96485 joules per volt mole, okay, times the ln of Q, right? So next thing we need to do is we need to figure out what the heck Q is. Well, Q, remember, is equal to products minus reactants, right? So products would be here, our platinum concentration. Okay. We also have iron, but it's a solid, so that doesn't go in there. We've got platinum that's a solid, so we've got iron 2+ down here. Okay. Let's go ahead and plug in those values. Platinum is 0.059 molar. Doesn't matter because they'll cancel. And then we've got our iron is 0.0021 molar on the bottom. So in that case, Q is equal to, let's see, what's Q equal to? 0.059 divided by 0.0021 is about 28.1. Okay, it's unitless. And so now we can go ahead and plug Q in up here, right? So let's go ahead and just erase Q, and let's put in 28.1. Sorry, squeezing it in there. Okay, so now I can go ahead and erase everything else because we don't need those anymore. And now we can literally just plug in everything, right? So in my calculator, E is equal to negative 1.62 minus that whole thing, right, times the natural log of 28.1. When I plugged this in, I found out that E is equal to about negative 1.66 volts. Okay, again, it's still negative. This is non-spontaneous. Now, what if I really wanted to use, to make this kind of battery and make it spontaneous? What I'd have to do is just do the reverse reaction, right? Take platinum ions and iron metal, turn it into platinum metal and iron ions. And so in that case, it would become spontaneous. It would have an E value of positive 1.66 under these, same conditions, right? All right, so a lot of stuff, right? There's a lot of kind of formulas in there, but hopefully it's starting to make some sense. And hopefully you're seeing that all of these things, K and E and delta G, they all factor into, the same thing, right? Which is just determining spontaneity. Okay, and this stuff is actually pretty useful because we use batteries in our everyday life, right? Now, just for fun, let's go ahead and let's go to our camera real quick. And let's go ahead and just do a quick little magic trick here, right? So I'm going to have you normally, oh, that's weird, there's a random 5 of diamonds there, okay. All right, so Normally I'd have someone do this, but I'll just go ahead and do it. So I'm going to have you cut wherever, right? So there, for instance, right? And so at this point, just to mark our place, we're going to go ahead and see if we can figure out what your card is. Now, I've seen magicians that do this cool thing where you take your card and then it magically transports into like a pack of gum or into a dinner roll or whatever. So let's see. So in this case, we went ahead and chose the 6 of hearts. That's what we cut to, okay? So we can just drop that back in. And then in the process, should be able to open this up. And instead I've just got gum, right? Didn't actually transport. But because this happens to be spontaneous, I mean, I know the reduction potential for the 6 of hearts happens to be pretty positive, right? So what happens is in this reaction, you can take your juicy fruit and you just change it into 6 of hearts, right? And at that point, your reaction's done. Okay, awesome. So hope that makes a lot of sense. I will see you next time.